That looks really cool tilted like that. I kind of like it.
Yes! Yes!
Yeah.
So, can we live with that crazy kind of tilt on the screen up there? Is
What?
that all right? All right, so I got everything in. I heard a notice over here. Veronica's like, wait a minute, why does my N say 1?
Yeah.
You got to remember, mathematically and statistically, there's a good reason for that. There's a good reason why it says 1, 2, but there's actually 2 good reasons.
Because it equals 1.
Good. The first thing it's doing, I'm going to run one of our stats with you guys. That's okay. So you got L. First of all, don't just press enter, right? It will give you numbers that are absolutely meaningless. This assumes right now that there are 11 results, 2 through 12. On average, you get a 7 with this meaningless standard deviation, because that assumes that everyone happens one time. So this is just like a weighted average. From back in the day, you've got to do L1 and L2 because it has to keep track of you see more 7s than 6s, you see more 6s than 5. That's why on the quiz you're turning in on Thursday, if you turn it in with the snowfall data, I gave you some good-sized hints on that one. To recalculate the average with February 8th snowfall on it, you have to weight the other 70 whatever years it was. You have to use that, whatever that number is, to weight the previous, what is it, 0.75 inches, I think, or 0.5 inches, or whatever it is, the old average counted over 75 years, and then you have to work in the 1 year where we got 25 inches of snow in a day. You can't just average 25 inches and a half an inch and say, on average, we got 12.5 inches of snow on February 8th. That means there was 2 years. 1 year we got a half an inch, 1 year we got 25 inches, and that, yes, that is indeed 12.5 inches on average per year. But we didn't get that. We got 75 years with an average of a half an inch, plus 1 year with an average of 25, so that 25 inches has to get spread evenly across all the other 70 lollipops. But it's a more ridiculous case. It's a case where you've got 76 people in front of the class, all of which have half a lollipop, except for one person who has 25. And that person with 25 has to spread his or her lollipops evenly to all the other people with half a lollipop. That's not going to give each person very much, is it? It's going to raise it a smidge, but it's not going to give them all that much. Does that make sense? You know what I'm getting at? That's the importance of L2. L2 is telling you how many lollipops each of the years has, in this case, how likely it is to get 2 or 3 and so forth. So one of our stats, L1, L2, boom, those the average is exactly the same. That goes back to what Nick said. It just so happens 7 is the middle sum. Thank you, sir. But what's different is the standard deviation changes. First of all, we've got a standard deviation of 2.4, yay us. No sample standard deviation. Thankfully, there shouldn't be one, should there?
No.
Because that's the population. That is the population of 2 dice. There is no sample. Now, the summation of 1, it's unfortunate that it's called n equals 1. I wish it said something else, but unfortunately that's what we're stuck with. What it did was it added up L2. And it said L2 equals 1. Well, it does, because the sum of the probabilities equals 1. So 100% of the time, you're going to land somewhere on this curve that just so happens to have an average of 7. Is that fair? Believable? Take a look at your data. Go ahead and graph it. So this is our make a histogram. I think a histogram is probably the best way of looking at it, personally, I think.
Zoom 9?
Zoom, assuming that your graph is set up properly, mine is, believe it or not.
Yeah.
This is late. If you hit Zoom 9, you get this. This is unfortunate. We can fix this. We can fix this. It doesn't like probability distributions very much compared to frequency ones, but we can futz with it and make it better. So press your window button. X min should definitely be 2. What do you think X max should be?
13.
Yes, 13. Very good. Make it 13, 1 more than the 12 that we know is the max value. And then make the scale equal to 1. And this might not work. We're going to try it. We might get an error with one. We may have to adjust it to something else. And then we're going to leave everything else the way it is. Y max, I think, is too big. Because remember what Y is? This is weird. You have to kind of switch gears with the TI here. If we're graphing on the vertical axis, what is actually being graphed on the vertical? Think about your distribution. The percentage, the probability. I heard 2 correct words that are analogous. So the biggest percentage we have is 17%. So I'm going to make it 0.2 as far as the max goes, if that's okay with you guys. Because the biggest one is going to go is 0.17. That gives us some wiggle room.
Right.
And then let's see if this works. It did. Ooh, we can actually cut the bottom if you want to make it look even better. That negative on the bottom is kind of crappy. Want to make that 0?
Yeah.
So you see, Zoom 9 got us in. The problem is Zoom 9, I don't understand why the TI goes to that window in Zoom 9. I don't get it. I don't understand.
Did it just hit graph again?
Then just hit graph. Every time you mess with the window, you're going to be pressing graph. Look at that beautiful thing. Look familiar? Yes.
Some kind of bell.
It's some kind of bell shape. Believe it or not, and you'll analyze this more on your last exam, it's more perfect than a bell. It's actually a perfectly linear absolute value function. And you think about why. Every probability goes up by 1/36. 1/36, 2/36, 3/36. So every 1 over goes up by 1/36. So, but it's bellish enough though, Pat. The skew on this thing is 0. There is no skew. You could use the 2 standard deviation rules to find outliers. You could use the 2 standard deviation rules to find outliers. So what you would do if you wanted to do that, and this is again looking forward to the quiz you're going to be doing on Thursday. If you wanted to use 2 standard deviations, just do the average of 7 plus or minus 2 standard deviations. Anything outside of that is going to be too big or too small.
So what was it, like 2.4?
It was 2.4, right? Think about that. Your standard deviation was 2.4. 2.4 doubled is 4.8. 7 plus or minus that. So 7 plus that is 11.8. That means 12 technically is considered an outlier. Boxcars shouldn't happen very often. It doesn't. 1 in 36.
Same the other one.
Same the other way. 2 also doesn't happen all that often. It happens 1 in 36 times. And there's a neat tie-in there between outlierish behavior and rate of occurrence. Notice when you look at the distribution, the only 2 outliers, the 2 and the 12, are the only ones whose percentages happen less than 5%. That's a neat, Di, you mentioned p-values you've been reading about in your psych journals. Whenever you guys read your psych journals, your social journals, your human development journals, your nursing journals, your pre-med journals, you'll very often see these things called p-values. P less than 5%, P less than 5%. Whenever something happens less than 5% of the time, it's considered to be kind of weird. So if it only happens 1 in 20 times or less, that's considered unusual, which we've been calling those outliers. Another way you can measure outliers pretty handily is by saying if it happens less than 5% of the time. That's why 2 and 12 are considered outliers in this case too. Fair? Pat, ask me that question.
Yeah, you know, we talk about rounding up or whatever.
Sure.
You don't want to do that.
Well, technically speaking, it's a good call. I mean, because if you round those up to 2, well, 2.4 would be rounded down, wouldn't it? That'd be rounded down to 2. Right?
Yeah.
So technically speaking, you go 7 plus or minus 4, which makes the outliers even clearer. But I see what you're saying. If you go 7 plus or minus 4.8, then those round up to...
Right. 5.
So one way to avoid any rounding issues is to go straight to the distribution and look at the ones at less than 5%. See, here Pat just said, his concern was when we do the mathematics on the 2 standard deviations, we get a range of values. Let me put this up. Let's just add it right to the graph. Thank you for this question. It's a very, very good one. Very, very subtle, but very, very, very good. So here's our graph. And Cassidy, I know you got a question, my friend. Let me get to you in a second, if you don't mind. You've been very patient. So here's what we know. We know that the average on this distribution, I'm going to call it mu if that's okay with you guys. Is that fair? Good. Mu, we see this okay? Yes. Is 7. The plus or minus around that's about 2.4. It's about 2.4. Okay. So if this is 7, there's 1, 2.4 brings us out to about here. Then 2 more of those essentially brings us out. It gets tricky because of where the scale is, but it essentially brings us out to right about here. So this would be 7 plus 2 times 2.4, which would be mu plus 2 sigma. Pretend that's a sigma. There. And then down here, mu minus 2 times 2.4 brings us down to mu minus 2 sigma. So if you throw up your fences, your fence goes from, what was it, minus 4.8, so 2.8 all the way up to 11.8.
8.
Did I do that wrong?
Yeah, that
2.2.
1.8, yeah.
2.2, I did the subtraction wrong. So your range of believable values goes from 2.2 to 11.8. Now, if you round those, that's 2 to 12. 2 to 12 covers everything on the die rolls, yes? But that's where it gets tricky when you get close to those fences. Do I call it an outlier or not? There's no concrete answer because there's no one concrete definition for what an outlier should be. I've given you 2, now I've technically given you 3 of them. Because now I'm saying you can also look at percentage of occurrence. If something doesn't occur very often, it's the definition of rare, correct? Rare means it doesn't happen all that often. So when it does happen, you go, whoa, that's kind of cool. So technically speaking, if you do round this, you lose the outside of the, right now 2 is outside of this, and 12 is outside of that, yeah? So what some students will do is they're like, you know what, that's all fine and dandy, this whole box plot thing. You also run a box plot on this to see if they're unusual. IQR, 2 standard deviations is all wonderful. What a lot of students will do is they'll just go over the distribution itself, and they'll say, okay, well, we got these new occurrences. This right here is less than 5%. That's rare. This right here is less than 5%, and that's rare. Everything else in there is greater than 5%, therefore it's expected.
Which would be captured in the 95%.
Essentially, yes, which roughly you're going to capture in the 95% in the middle. And it's almost perfect with a pair of dice, because the 2 ends are roughly 2.5% each, aren't they? They're a little bit more, but they're roughly 2.777, I believe, was the percentage on Snake. This is 2.777%, and so is that, I think. And if you add those together, that's just about 5%, which means everything else in here represents the normal, usual, middle 95%. Even though it's not a perfect bell curve, it's not perfect. It's a little thick on the ends. It should be more tapered, but it's bellish enough. Is that fair, Pat? That's a very, very good question, a subtle question. Very, very good one. Cassidy, you've been so patient. Go, my friend.
I just couldn't figure out how to get my graph.
Oh, check that out. Can I see what you got there? I think it's just your window. Oh, L1, L2. So when you have your plot set up right there, make sure the frequency's on L2. Yes. So this will happen very often. You'll try to graph this thing, and you'll get a horizontal line. Bar, 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 horizontal. That means you're making it uniform. You got to make sure the L2 talks about the distribution.
What about if it just makes a mini version?
That's a win. Thank you, Marty. If you just makes a mini version, that just means I'll see if I can make your mini version as well. Something like that.
Yeah.
Ish. All you want to do then is you want to get rid of all this dead space that's right here. So, oh, actually, let's swing this. Swing the camera back over so everybody can see what we're doing. Yeah, that's just a window adjustment. So press your window button, and here's where this calls a little bit on all our old skills from back in the day when we had like Mac 95, maybe Mac 111. Sorry, bring back dead memories. But just press your window button. X's are set up perfectly right now. It's the Y's that are the problem. So then you have to ask yourself, what's the biggest Y value I've seen? What's the biggest Y value that I've seen so far? Well, the biggest Y value is for 7, it's 1/6, or 6/36, which is about 17%. So right now it's at 100%. I would change that. I changed it to 0.2, which gives us a little bit of wiggle room. And then when you press graph, you should get a pretty nice full window. Cool? And you can always finagle. You can finagle that all you want. Believable? Maybe? A little bit-ish. Getting there. Joe's getting there. He's starting by. Other questions? Give me some questions. Di, go.
How come it wouldn't be less than 2.5%?
This is a fantastic question. Di is saying, wait a minute, timeout rule. Damn it. She didn't swear. She wants to, it's okay. So I just drew a box around this middle 95%-ish. So if that's 95% in the middle, it seems to be these two pieces should be total of 5%, which would mean each piece should be less than 2.5%, not less than 5%. I love what you're saying. What I'm trying to get at, and this will make more sense with the result we're about to look with the coin flips, any event that comes in under 5% is suspect of unusual behavior. Not just with symmetric distributions. We're about to generate one that is definitely not symmetric. So we saw a uniform distribution, we've now seen a perfectly symmetric bell-ish distribution. It'll work in any distribution, not just the ones that are bell. What you said works perfectly always for bell curves. But the less than 5% thing, very good question. The less than 5% thing works for all curves, not just the bell ones. Does that make sense? Because you're in your mind, you're like, wait, that's 105%. That doesn't make sense. Good. No, good. That's good that you're thinking that. But the less than 5, it's an industry standard. Whenever you're reading your journals, P is less than 5%, less than 5%. They're using this idea as you're reading those journals. Good. Very good question. All the ones you got. I want to switch to coins now. So here's what we're going to do. Make sure I get the right one. Yes. Grab your coin. Marty, go!
So before you switch to coins.
Before we switch to coins, ask me that question.
Okay, so when you were getting your little gates on the
Yes!
here, so you were taking the average.
Plus or minus the 2 standard deviations.
Okay.
Is that fair?
Yes.
And the standard deviation is about 2.4.
And so rather than using XX, we're using that sigma X.
You have to because you can't use S. There is no S. Right?
Right.
And now you can remember the little trick. It depends on if you guys did the variation quiz. The little shortcut trick with X bar plus or minus 2 S's. You can use that here. Just switch it to sigma instead of S.
Okay.
Is that fair?
And that would be specific only to this experiment?
Only to any probability distribution. When you've got a probability distribution graphed here, you have to use sigma because there is no S anymore. Is that fair? Believable? Ish. Getting there, maybe. We're getting there.
Does this work for a non-bell shaped?
Yes! The less than 5%? Yes!
As long as-
Because if it's not bell-shaped, we have to throw out the plus or minus 2 sigmas, don't we? The plus or minus 2 sigma, the only reason, I'm sorry I brought it up, I think I'm pissing people off. The plus or minus 2 sigma thing, I'm only bringing that out right now because this is roughly bell-shaped data. If you don't have bell-shaped data, the same rules apply as before. You can't do that. This looks pretty bell-shaped, yes?
Yeah.
As soon as it's not bell-shaped, we can't do that anymore. Then we gotta go IQR, or we gotta go just less than 5%. Those will still work with any distribution. Oh, good, please check in, that's good. So that whole 2%, or that 2 standard deviation thing, only happens because this roughly looks like a bell curve. Let's make one that doesn't. Does that make sense? Go ahead, Marty.
One more question.
No, go ahead.
I apologize.
Don't you apologize.
You probably said this already, but why did you take off the first and the last one?
Oh, they're technically outside of these numbers. So 2 is less than 2.2, and 12, and not so much take them out, just identify them as rare. Like those are the outliers, if you wanted to call them outliers by this definition.
Okay.
Does that make sense? So, now I'm not saying we throw them away, because I mean, hell, a lot of gambling games are dependent upon them. As a matter of fact, how you deal with snake eyes in craps is very important for the casinos, depending on if you're betting with the roller or betting against the roller. I forget what that's called. You guys had to analyze it last term. A field bet, a pass or a don't pass bet.
Yeah.
So craps is extraordinarily intricate as far as how the betting works. But if you're rolling, you can do a pass bet, and there's a series of rules that goes with that. And snake eyes is bad, obviously.
You
Snake
can
eyes
actually
is
bet
bad on a
against
pass bet.
yourself.
Say that again.
You can actually bet against
You can
yourself.
bet against yourself, exactly. And if you're betting against the roller, that's called a don't pass bet. But snake eyes actually works flip-flopped for that because they have to take that 1/36th and switch it around to make sure on average they make money on you. That's how it has to work. And so that, I'm not saying throw the 2 away, I'm just saying realize how rarely it happens. But keep track of it. Is that fair?
Yeah.
Good. Good. Let's make some non-bell shaped data. Yes, baby? Yes, grab your coin. Here's what I want you to do. And do this, I'd say do it like 10 times each. Flip the coin until you get heads. And then stop. But keep track of how many times it takes you to get heads each time. Does that make sense? So if you flip and get heads, that's 1. If you flip tails and then heads, that's 2. If you go tails, 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 heads, that's like 14 or something. I've lost track. But you see what I'm getting at? So do it like 10 times. So flip until you get 10 heads and keep track of how many times it takes each.